Recorded is rolling. It is Tuesday, October 4th. So let's wrap up Unit 2 Dynamics today with a couple activities. You guys have a packet on your desk. Do you guys see this packet? It has AP style questions. There's a couple of them here. We're gonna get to that. Take this packet. Did you guys write your name on the packet? You guys write your name on your packet. Okay. All right. All right. So, did you guys write your name on your packet? All right. Then on the back side, see how it's mostly blank. Somewhere near the bottom, do this. Here. Do you guys also see some spring cells on your desk? Now, pick up one that's not brown. See how I have a brown one? But there are lots of colors, right? All right. So, did you guys find one that's not brown? Okay. Then near the bottom of this page, so on the back of the packet, down near the bottom, right? Okay. And then as a subscript, do the color that you're holding that's not the brown one. Now I'm going to do brown because I have a brown one. But you guys found a spring cell that's not brown. Okay. And say equals. All right. And here's how this activity is going to go. We're going to figure out what is the spring scale of the spring inside your what's the spring constant of the spring in the spring scale? Okay, but like how stiff is it? Which relates back to something we did right at the beginning of this this unit, which was Hooke's law. You guys remember Hooke's law? Hooke's law relates how much does a spring stretch or compress? Give it compress, but in this case stretch, given some force. Also, if you know how stiff it is. So if you have some spring that's unstretched like this, there's a poster hanging from my ceiling that looks like this, right? Hey, you have an unstretched spring, then you put a force on it. Like a stretching force. Here's force, here's the equal and opposite force over here. It'll stretch it by some amount. And I'm calling that amount that stretches X. And guys, what's the formula that relates that force to that stretch amount? Equals KX. There you go. Right? Where that's Hooke's law right there, right? Okay. Now, if you know the force that you put on it, which you can because I mean this is a spring scale, it tells you how much force you're putting on it, right? And you know how much it stretches because you guys have rulers at your desk, right? Can you go check, and then solve for K? Can you guys see that? Right. Here's the answer in terms of variables. How much force divided by how much it stretches. And it's a linear relationship. So you could get like 5 different data points and graph them and like this could be a y equals mx type graph, isn't it? Right. But really you only need one data point because it's a direct relationship. So I will do it for the brown scale. You guys can do it for whatever scale you have that's not brown. And let's see. So let's see. I know if I put on 10 newtons of force, that would max out the scale, and I have to stretch it some amount. How much is that amount? Well, let's break out the ruler here. Looks like to go up to 10 newtons, it's going to take 5.2 centimeters. I'm looking at 5.2 centimeters. So if I put 10 newtons on 5.2 centimeters, okay. See if I divide that out right now, 10 over 5.2, couldn't I call that 1.92 newtons per centimeter? I could do that. Now, usually spring constant in this class, you see not newtons per centimeter, but newtons per meter, right? Can you guys do some dimensional analysis? Maybe I'll throw in some railroad tracks here. You get newtons per meter. I know that there are 100 centimeters per every 1 meter. Okay. So multiply this by 100. Okay. And I can say the K for the brown scale is 192 newtons per meter. There you go. There's the spring constant in this spring scale right here. It's 192 newtons per meter. Okay. Okay, so back to a page. I would show my work for that. I would just basically copy this right here. I should have done this on this page. Okay. I'm getting 192 newtons per meter. Okay. Now, if you have a blue scale or a green scale, you should be getting a number that's a little bit less than that. And if you have a red scale or a white scale, you should be getting a number that's a little bit more than that. Okay. So go ahead, do your work just like I did here. Put it at the bottom of this packet on the back. Okay. Let me take an update over here real fast while you guys are wrapping that up. Okay. All right, so did everybody get the spring constant for a scale that's not brown? Okay. And you guys showed your work, and you guys have the answer on your packet. You guys got that? All right, you guys good? All right, here. So, okay, if you're having trouble with the, see, it tells you how many newtons that you're pulling. You guys are looking at newtons, not grams, right? You guys are looking at newtons, right? So, like on the scale, I see if I apply 10 newtons, it's going to stretch this much. How much is this much? Well, I broke out this ruler, and to stretch up to 10 newtons, that's 5.2 centimeters, right? So if I take Hooke's law and I rearrange it algebraically, the force divided by the stretch amount tells me the spring constant. That's how stiff the spring is. It's a way to quantify how stiff, right? Okay. And it for 10 newtons of force, it stretches 5.2 centimeters, right? So I could divide that out and get newtons per centimeter. Maybe I want newtons per meter because that's a more conventional way to express the spring constant. So I can do a little conversion, just multiply by 100 centimeters per meter, right? And I come out with 192 newtons per meter, right? So if this was like a really long spring and it was equally stiff, if I put 192 newtons of force on it, it would stretch exactly 1 meter, right? Now you have to have a crazy long spring for that to happen, but okay, you guys get the idea, right? If it was equally stiff. Okay. Now the brown scale is kind of a medium stiffness, right? The green and blue scales are less stiff. You put a little force, it stretches a lot. And the red and white scales are really stiff. So you put on a lot of force and only stretches a little, right? Okay. And the gold scale. If you have a gold scale, that's also stiffer than the brown scale. So you should get a number that's larger than my number. Yeah. The white scale should be larger than this number. Yeah. I don't know the exact numbers. I just know it's bigger than this number. Okay. All right. All right. Who has any question? Any question? Is that working out for you guys? Worked out? Okay. All right. All right. I'll flip over to the front here. So there's two long style FRQs here. Now these are not officially released by AP, so that's all right there. Equally difficult type content. All right, so let's go through these. You guys have color pencils on your desk? I think we will do this. We'll do this a little bit at a time, and then I'll have you guys grade yourselves, and we'll see how much we can fill up, or how many we can do in the classroom we have. Okay. A block of mass M rests on an air table. Ooh, hey, look, air hockey table. No friction, right? Okay. And is pulled with a force probe. I think they're implying pulled horizontally, but right. Producing the force versus acceleration graph. Oh, look at that. So with different forces, there's different accelerations. Right? Now, if you think about like cause effect, maybe we want to flip those axes, what's independent or dependent variable. But actually, I like the way they put force on the vertical and acceleration on the horizontal, because that aligns with the formula that's going to help you answer this question very quickly. Determine the mass of the block. All right, so give you guys a minute. See if you guys can figure that out. Everybody figure out the mass of the block based on that graph. All right, and write it down. I've got the answer right here, so make sure everybody gets that. Yes.
So for Hooke's law, is the displacement in centimeters?
Yeah, displacement can be in centimeters. Now, if you do displacement in centimeters, you're calculating. Okay, all right. Why you guys get that? Let me go back and answer this. Okay. So I stretched 5.2 centimeters for 10 newtons. So if you divide that out, you get 1.92 newtons per centimeter.
Okay.
Right. And then if you convert to meters, multiply 100 centimeters per meter, you get 192 newtons per meter. Okay. All right. Did you guys all figure out the mass of the block? What did you guys get for the mass of the block? 3 kilograms. 3 kilograms. Good. All right. So, all right. You guys got the color pencil? You guys got a color pencil? I put a stack of color pencils on each group desk. All right. Here we go. This is going to be out of 12 points total. All right. So, yep, the answer is definitely 3 kilograms. You guys figured out by doing F equals ma. It's just Newton's second law of motion, right? F equals ma. So, if you rearrange, here, let me write this bigger, but works better for the camera. Here's Newton's second law of motion, right? A lot of times I write it A equals F over M, but you guys get the idea. Okay. But if you're solving for the mass, wouldn't mass be force divided by acceleration? Right. Now it's a direct relationship, so you can pick any point. What they did was, looks like they did a rise over run, like the slope of this line. It would also be the slope of that line, wouldn't it? Right. That slope of the line. If this is your independent variable, that's your dependent variable. The slope of the line, independent, dependent slope of the line is the slope, is mass. Right. All right. So 1 point for indication that the mass of the block is equal to the slope of force versus acceleration. Right. So if you do like a rise or run, that'll do that. Okay. 1 point for choosing 2 points on the graph and calculating the slope, and 1 point for the correct answer with units. Yeah.
So did we have to do it for slope, or could we have used the equation?
You know what? I think it comes down to like how generous is the grader at that point. Like if I'm grading it, I would give you all credit. So if you came up with 3 kilograms, I'd say, okay, well maybe you picked an origin point as one of your points. So yeah, I would give you all 3 points if you got 3 kilograms. Okay. All right. But yeah, AP does like this this method of like calculating slope. So yeah, definitely be ready to field something like that or create something like that yourself. Oh yeah. 1, 2, 3. Yeah, 3 points. Right. Okay. The block is now placed on a rough horizontal board having coefficient of static friction of 0.5 and coefficient of kinetic friction of 0.3. Right? A horizontal force of 10 newtons is then exerted on the block. What is the acceleration of the block? And justify your answer. Right, so you need to come up with the numerical answer, right? And then where it says justify, maybe like write out a brief sentence like, okay, it's because blah, blah, blah. All right, who thinks they know the answer? Who thinks they know the answer? No. What'd you get?
1/3.
What's the units for acceleration?
Oh, meters per second.
Meters per second squared would be the unit. What'd you get? Okay, I'm looking for something else. You got something else. What'd you get? Looking for something else. Base? No? Nobody got something different than any of those? Let's go through this process. Let's do a free body diagram. I'll walk you guys through the answer. Okay. Oh yeah, what'd you get? Ooh. I think you're onto something. All right, I think you're on the right track here. Yeah. let's try this out. So I know this block has a weight mg. In fact, you guys know what mg is because you guys know mass is how many kilograms down? 3. Now that's gonna be important. So what's the weight of the block in newtons? 30 newtons, right? You got 30 newtons of weight. Ah, if the weight's 30 newtons, then what's the normal force? Also 30 newtons, right? Because we're only pulling on the block horizontally, so that's not going to change what's going on vertically. Okay. It said we put on a force of 10 newtons. That'd be about a third of that, right? So F pull wait, pulling, I think, something like that. 10 newtons, right? Okay. What's the what is the maximum static friction force that it could possibly build up to? Here. So you guys remember force of friction? We go straight to right here. Remember, it's an inequality. It's less than or equal to coefficient of friction times the normal force. Because remember, there's 2 different kinds of coefficient of friction. In fact, they gave you both in the setup, right? There's static friction and kinetic friction, right? So if you ever have kinetic, where you know for sure it's sliding, if 2 surfaces of slide past each other, you just turn that into equals and use coefficient of kinetic friction where it says mu, right? But if you start from rest, you have to make sure that you overcame the initial friction, right? So that runs into the inequality situation. So let's check this out. Force friction, I'll say less than or equal to for the static friction case times the normal force, right? Okay. Now, they told you coefficient of kinetic friction was, say, 0.3 and static was 0.5. Yeah. Mu k is 0.3, mu s is 0.5. Right. Right. So since we're like, see if you start from rest and you apply a force to start to drag it, let's see what it could build up to. Right. So at a maximum case, I'll say force of friction, static max. Right. That would be 0.5 times the normal force of 30 newtons. Ah, is that like 15 newtons? Is that true? Right? You know what that means? That means that if you're, say if you apply a force like 1 Newton, little tiny force, 1 Newton, is that block going to move? No, right? If you apply 2 newtons, is that block going to move? No. What force do you have to apply before it finally breaks friction and starts sliding? 15 newtons. Right? Yeah, go ahead.
F and why not F4? Because aren't we just sliding the block for 45?
Yeah. What I'm trying to figure out is something about this friction force here, F sub FR. Right now, if you start from rest, here, no, let's say you are sliding because yesterday you guys had a, or hold on, so recently you guys did a lab where it was like sliding across surface, right? Now, if it's sliding at constant velocity, then you can say for sure that you have a balanced free body diagram, right? So all the forces equal out. It looks a lot like that. Okay. What about before it starts moving? What if I put a little tiny force? Do you think that there's a little tiny friction that automatically builds up? And what if I double the little tiny force to a slightly bigger tiny force? Right? You think that friction is automatically going to respond, right? And it's going to keep building up, building up, building up. You know, 3 newtons, 3 newtons, 4 newtons, 4 newtons, 5 newtons, 5 newtons, right? But it's still going to stay stuck to the page, right? It's not going to move, right? Until you finally hit 15 newtons, right? And that's where the static friction like maxes out and then say, okay, well, I can't do anything. If you do 15.01 newtons, it's gonna bam, it's gonna break friction and start sliding. Right? It can only go up to 15 newtons of friction force. Okay. So yeah, so anything up to 15 newtons of pulling, the friction's automatically gonna respond and just cancel it out. Okay. So it never breaks static friction. So what's the acceleration of the block then? 0, 0. Okay. Now, if it were in motion, the 10 newtons would be enough just to keep it in motion because 10 is a third of the weight, therefore a third of the normal force, and it would be able to overcome kinetic friction, but not the static friction. So yeah, it's not actually moving yet. So here's how we're scoring this one. All right, this was for 3 points. 1 point for stating that the block remains at rest. 1 point for correctly calculating the static frictional force, which it was like 15 newtons. Remember, go up to 15 newtons. If you haven't hit 15 newtons yet, then it's just still stuck at rest, right? And then one point for correct justification. What they say? Oh, look what they got here. So they did the same thing I did, right? So mu times normal force, and then mu times mg, because mg is the normal force, right? They also got 15 newtons, just like I showed you, right? And then here's their justification. They got a little sentence here. It says the 10 Newton horizontal force exerted on the block cannot overcome the static frictional force of 15 newtons, and the block remains at rest. Okay. All right. All right. All right. You guys get it? All right. All right. So continue on there. So let you guys know that answer. Moving on. Okay. A second block with twice the mass and twice the surface area as the original block is placed in the same horizontal board as the original block. One end of the level board is now slowly raised. Ah, that's what you guys did. Remember the second half of your lab yesterday? You had that incline half, right? Which block, if any, is the first to slip and begin sliding down the board? Justify your answer. Equations may be part of your reasoning, but equations alone are not sufficient justification. So yeah, you can refer to equations. That's all fine and good, but also write out some kind of sentence answer. All right, so give you guys a little time to do that.
Does surface area affect the coefficient of friction?
That is a good question. I was gonna see how you guys would feel that. Did you guys know the answer to that question? Does the surface area affect the friction at all? No, that's a total red herring detail. So they didn't have to say anything about surface area. Okay. So it turns out if you double the surface area, you may say, well, the friction acts over a larger area, so maybe that would like slow it down or something. But the weight doesn't change, and so the normal force doesn't change. It like cancels out, right? I guess there's like less pressure per, right? But, yeah, so surface area doesn't matter. Okay, while you guys are wrapping up your answer, let me see, show of hands what you guys thought. I'll narrow it down to 3 possibilities as to which one breaks friction and starts sliding down first. See, possibility A, maybe the small one breaks friction first. Possibility B, maybe the large one breaks friction first. And possibility C is, well, maybe they're identical motion. Right? Maybe they break at the same time, right? Same angle. So show of hands. How many guys say the small one breaks friction first? Small one. Show of hands. How many guys went with the big one? Big one first. And how many guys said at the same time for the same angle? Ah, yeah, because that's exactly what you guys saw yesterday too, right? Right. The only difference between this question and what you did yesterday was yesterday we were more focused on like kinetic friction, like sliding at a constant velocity. Okay. But if you tweak the framing a little bit from your lab yesterday, you could say like, what angle does it break friction? And that also does cancel out. Let me show you guys your notes from yesterday. Well, I think another class notes, but basically the same thing, right? Remember, you guys are trying to figure out coefficient of kinetic friction between the 2 surfaces. That was your target question. But if you replace that with static, then it would just be what angle does it initially break the friction, right? And here is for the horizontal case where it was real straightforward, just the ratio of these 2 forces, right? Friction over normal force. Okay, so you can take that same expression and also apply it to this incline case. So it's still friction over normal force, and we're interested in what angle does that initially break friction. And remember, if you do this setup, right, this setup right there, right, and then substitute in these values because the normal force, well, that is mg sine cosine theta, and the friction force is mg sine theta, right? Remember that mg cancels out, right? So not only does the mass cancel out, but also the gravity field. Like you could take this to the moon and you get the exact same answer, right? You guys remember this? Mu is equal to tan theta, right? Now yesterday it was mu k because it was sliding down constant velocity. Okay. For you guys today, you could call that mu s, and this theta would represent the angle that it initially breaks friction, which would actually be a little bit bigger than the angle to keep it down at constant velocity. Okay. How many of you guys figured out what angle that is? Since you guys got calculators on your desk, you figured out exactly what angle. Does anybody know? How about this? Coefficient of static friction, that was 0.5, right? Can you guys calculate the angle if you know that this number is 0.5? What do you do to both sides?
Inverse tangent.
Inverse tan. You know, you do inverse tan 0.5 on your calculators. What is inverse tan of 0.5? Right, here's your 0.5. We're solving for this angle. That's why I did inverse tan, right? Right. About 26 point something degrees, 27 degrees, something like that. Look at that. All right, let's check out their solutions. So they counted this one out of 3 points also. You guys got those colored pencils? Let's check this out. They did 1 point for stating that both blocks slip at the same angle. 1 point for recognizing that the parallel component of the gravity force and static frictional force are equal and both blocks do not slip initially. I don't think it's technically exactly correct, but it's the right idea, right? If you divide by mass, same effect. 1 point for recognizing that when the static frictional force reaches its maximum value, both blocks will slip since theta max is independent of mass, right? Because mass cancels out. And that's what I was just showing you right over here. In fact, the mass cancels out, right? Okay. Now they were also looking for a sentence form explanation. So let's see their full example answer. This is their example answer right here. They said both the gravitational force and static frictional force are proportional to mass. It's true, right? Triple the mass, you'll triple all the forces. When one end of the board is slowly raised, the blocks do not slip, since the magnitude of the static frictional force is equal to the parallel component of the gravity force acting on the board. So the force of static friction is equal to mg sine theta. That's just saying that as you ramp up this angle more, right, this friction, well, here, you guys know that the sine component of the weight is going to grow bigger, but this friction will, since it's static friction, will automatically respond and also grow in kind with us. It'll smash it, right? As the board continues to be raised, however, the static frictional force reaches its maximum possible value at mu mg cosine theta max, at theta max. the gravitational frictional forces still balance, so that, okay, mg sine theta max is equal to mu mg cosine theta max. Mu is equal to, right, and it just turns into basically this right here. Okay, just finish that. So mu sub s is equal to tan theta max, and the angle theta max is independent of the mass. So both blocks will slip at the same angle. Okay. And in this case, theta max, oh yeah, it's 26 point something degrees. That's what you guys found. Look at that. Okay. And you guys know how you got it too. You did inverse tan of 0.5. Okay. You should have thrown that in there too. Okay. You guys good? Part D, which block, if any, has the greater acceleration? Okay, so this is once they've broken friction and they're starting to slide down. Okay, now, since I can't tell you that they would both be accelerating, right? So to keep them at constant velocity, you would actually have to tip the angle down a little bit, right? Because kinetic friction is coefficient of kinetic friction is less than coefficient of static friction, right? So they are both accelerating. Now, which one is accelerating more? Calculate the acceleration and then justify your answer. Okay. Show of hands. How many guys know the acceleration? Who figured out the acceleration? Ooh, all right, give you guys a little more time. I'm just gonna figure out the acceleration. Okay. Throw you guys a hand if you're like super stuck. remember there's two approaches to acceleration. The old way, going back a few weeks ago, is, well, you know, some of the velocities and times and displacement, that's all kinematic stuff, right? That's not what we're doing today, but yeah, that could be a question in the future. How do you get acceleration? Well, it went so far and so much time starting from rest left. The new way of getting acceleration is Newton's second law of motion. You have to know net forces and masses, and then divide those two. See, if I have a net force acting on some mass, right? Can I figure out the net force and the mass and divide those two? Bet you guys can do that, right? What'd you get?
I don't know how to justify, but using my equation, I got that I have the same acceleration.
Same acceleration. How many guys got same acceleration? Right. All right. So you guys see same acceleration, right? Right. Who got a number? Who got a number? What'd you get?
1.8 meters per second.
All right. Who got what Leonardo got? 1.8 meters per second squared. 1.8. Yeah. Yeah. All right. Winners. Winners. All right. There you go. All right. So again, here's the free body diagram for it. And now this is from yesterday. The only thing you have to change is kinetic is now static, right? It's the same idea, right? So there's going to be some, sorry, the other thing to change too is that it's no longer in equilibrium exactly, right? Because this, remember, we found this breaking point, this 26.6 degree angle, where that was just enough to overcome the static friction. But now that we've overcome static friction and it's sliding, aren't we playing off coefficient of kinetic friction? So didn't this friction shrink a little bit? Right. So this mg sine theta driving the block down the incline and the friction holding it back are no longer equal. Right. And this guy's going to beat this guy. Isn't that true? Now that it's jumped from static to kinetic. Right. Is that true? So the block is no longer in equilibrium, although it will look very similar to this. You could take a difference between these two forces. There's now larger force than this, right? And that would be the net force. So wouldn't the net force be mg sine theta minus the friction force, right? The friction force is still coefficient of friction times the normal force, and normal force is still mg cosine theta, right? But they're just no longer balanced. Okay, is that right? Okay, let me get that on paper here. I'll show you guys exactly my work, and then we'll go over and look at how they squared it. Okay, so everything's going to feed into Newton's second law of motion, right? Where the net force is, oh, hey, look at that. There's the sine component, the weight pulling it down. Say, hey, let's accelerate down the incline. And here's coefficient of kinetic friction now times the normal force. Look, normal force I substituted in mg cosine theta, right? And that's what's causing that mass to accelerate, right? This is Newton's second law of motion. Here's your net force equals mass times acceleration, right? Now, if you divide both sides by m, well, you guys see the m's going to cancel out, right? So I have three terms, boink, boink, boink. You guys see three terms? Okay. Here's a term, here's a term, here's a term. And they all have the m in them. So you could divide both sides by m. The m cancels out, right? That's why they're going to accelerate the same. So this is mass independent, right? Okay. So the acceleration, here I just swap the sides. The acceleration is just this minus this, right? If you want to, you can factor out the g. I guess you don't have to, right? But we know what the angle is because we already figured out 26.6 degrees. That's where it breaks friction and starts sliding, right? Right. So let's pop in 26.6 degrees, right? You could do 9.8 or 10 meters per second squared, right? They'll take either one, right? And then we're going to put in 0.3 for the coefficient of kinetic friction, right? And right, and that's well, that's what Leonardo got, right? And so some of you guys too said, oh yeah, I got 1.8 meters per second squared, right? Hey, what would happen if you put in the original coefficient of static friction which was 0.5? What would this work out to be? I bet it would come out to exactly 0, right? But you can try that too. Well, the 26.6 degrees is around it a tiny bit, but it would be extremely close to 0 if you plug in 0.5 for the coefficient of static friction. Okay. All right, you guys get there? Okay. All right. So recap that one while you guys are writing that down, digesting that. When they say, what's the acceleration? It could have been a kinematic question, but it's not. It's a dynamics question because we've got forces acting on mass, right? So I have to find the net force, which is this force minus this force, which are no longer balanced. So this minus this, there's your net force, right? Three terms, they all have the mass in them. So at some point, mass is going to cancel out, right? and then you just substitute in the values because you have some numbers. They'll feed in, and then you get a number. 1 point, and this number has units, right? You guys remember all physics variables have units attached to them, right? Right, well, except for like coefficient, friction, that could be a unitless value. But meters per second squared describes an acceleration, right? Whenever you guys are describing acceleration, you're going to do meters per second squared, right? Okay. Right, you guys good? All right. Oh, sorry, I forgot to show you guys how to score that. So this was also worth 3 points. 1 point for stating that both blocks will have the same acceleration. Okay. 1 point for proper justification, such as acceleration is independent of mass. Mass cancels out at some point. And the last point for calculating the acceleration using coefficient of kinetic friction, you had to plug in 0.30 for coefficient of kinetic friction. Right? You should have gotten 1.8 meters per second squared. So here's their example answer. Both blocks have the same acceleration, since the acceleration is independent of mass. They set up a second law of motion. They did substitute some values. They just solved the answer in terms of variables, but you guys know the actual number answer too. Here, all right. You know what? All right, we got about 7 minutes of class left. That's enough to at least look at the next one. So let's just walk through this next one together. Okay, we got. So you guys score yourself out of 12. Okay. All right. So we'll just do this next one informally. 2 blocks, both mass 0.5 kilograms, are connected to each other by a thin string passed over a pulley, as shown in this diagram. Block 1 sits on a rough horizontal section, meaning that there's friction. Oh, the coefficient of static friction is 0.6, the coefficient of kinetic friction is 0.4. Guys got that? Check, check. Block 2 sits on a frictionless incline, makes angle theta with a horizontal. On the diagram below, draw a free-body diagram for block 2. Well, actually, I broke up. This is the answer key right here, right? So block 2, it's going to have a weight pulling down. It's going to have a normal force up to the right and a tension force up to the left, right? Now, you know what I would do, any next analysis step, I would take this weight and break it into components. I would call this weight mg, and then say mg cosine theta, mg sine theta, and then whatever analysis I had to do from there. I use F sub n as normal force, F sub t for tension force, but there's different ways to show those things, right? Part B, determine the maximum angle theta that the incline can make without the block sliding down. Well, I'm thinking what's keeping the block in check is the friction force from block 1. And isn't friction force coefficient of static friction times the normal force, or the normal force would just be the weight, right? So that would be what's holding it in place. And the force that's trying to drive the blocks into motion, wouldn't it just be the sine component of the weight of block 2, right? And those would have to be balanced for that to work out. I think it's better they draw this one out here. Okay. So I'm thinking the weight of block 2 times sine theta, isn't that what's trying to get it in motion? Here, kind of like this right here, m2g sine theta, right? So I'm gonna say the sum of the forces is equal to 0 newtons, right? And I'm just looking at the whole system. So m2g sine theta, right? And then, minus, and then the friction force from block 1, isn't that coefficient of static friction times normal force, which is just the weight of block 1, right? That has to 0 out. Would that be true? You set up something like that, right? And they said solve for theta, right? Solve for that theta. Can we do that? Add this over. Okay, so m2g sine theta is equal to coefficient of friction times m1g. Okay. Sine of theta is this expression. So if it, right. Oh, the gravity of the planet cancels out, so that's kind of nice, right? Okay. Isn't theta just going to be inverse sine of coefficient of static friction times the ratio of the masses, like that? Okay. Did they give you? Oh, they're the same mass. They're the same mass. So the ratio of the two masses would just be 1, right? And then coefficient of static friction was given as 0.6. So what is inverse sine of 0.6? And that is, oh, hey, that's a very special angle. 36.9 degrees. Look at that. We're talking about like a 345 proportional triangle, aren't we? So I definitely recognize that angle. that okay? All right, surprise 3, 4, 5, Pythagorean. Okay. I know we're short on time, so just skip through here. What's the next question? Part C. Part C says when the maximum angle, okay, actually we're good. This is the last question. When the maximum angle is exceeded, the blocks move. Does the tension in the string increase, decrease, or remain the same? Justify your answer. I'm thinking that once it's in motion, the fact that it is accelerating, I think it's going to alleviate some of the tension. Let's see what they, yeah. All right. So they said the tension must decrease before the maximum angle is exceeded. Blocks 1 and 2 are at rest. The tension string is equal to the parallel component of the weight. They should have said the weight of block 2. So the tension would just be mg sine theta, right? Before they start moving, right? Now, once they start moving, specifically because they're accelerating, right? Then it's kind of like that elevator situation, right? Like an elevator in partial free fall, the tension in the cable is going to be a little bit less than the weight of the elevator. Right? It's one of these posters up here, right? Picture. It's kind of like that, just on an angle. Right. All right. All right. So you guys get there? All right. So throw your page in the grade tray. And that is a wrap on today. Oh yeah, did you guys turn in your take home quiz too? Right. So you guys know quarter 1 ends this week. So yeah, if you guys got homework paid, if you guys turned in your quiz yesterday, I got that graded last night. So your grade's in the grade, but if you haven't turned that in yet, then I need that soon because it's about to close. Yeah.
So